Hello. I'm building a model of the bee brain, and I was at a conference recently talking about what I do, and I got a question, do bees have brains? And I went off on this mortified, pearl-clutching tirade of how could anybody in 2017 possibly imagine that blah, 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 blah. And as usual, it took my husband to talk me down and point out that there are plenty of good reasons why intelligent, well-educated, normal people, emphasis not you, may not have thought much about bees and their brains. So this is my attempt to explain what I'm doing and why. Now, that's a model of that's an image of the bee brain created by Angelique Polk. And to key you into this scale, that black bar at the bottom is 1 millimeter. So we're looking at a millimetrically scaled structure. But what I want you to focus on is, first of all, the intrinsic beauty of this, but also its complexity. So the bee brain is small, but the bee brain is not simple. The bee brain, like all brains, is made up of neurons. Neurons are just nerve cells, which are cells that are specialized to make connections and transmit information. And even in a brain this small, there's just shy of 1 million neurons. Now, I'm making a model of this. Now, that doesn't mean I'm sitting in a shed making it out of matchsticks. I would like to do that, but I wouldn't get paid to do that. So my model looks like this. So this is a model I've made with my colleague Alex Cope of part of the bee brain. It's a high-level abstraction. It's a computational model where each neuron or group of neurons is represented as a connection that transmits information. So it's a model of the brain as an information flow network. Now, why am I doing this? Well, I want you to think back to the last time you had an encounter with a bee, however that went for you. Where you may have got stung, that was probably your fault. But what you will have realized in that is that bees are smart. They are incredibly smart. And to show you just how smart, look at this video from Lars Chitka, Olli Lukala, and Clint Perry. So this bee has learned that if it moves that yellow ball into the yellow circle, the well beneath the ball fills up with nectar, and it gets a drink. And that's a bee. Now, if you wanted to, you could describe that as a form of tool use. And all of that intelligence, all of that smarts, comes somehow from the bee brain. And I want to understand this bee level of intelligence. But to do that, I've got to understand how the bee brain works. And that's a mighty question, even for something like a bee brain. So how can we go about dealing with a question with that kind of complexity? Well, one approach would be we could take the brain to simpler bits, we could work out what the bits do, and then put it back together. The problem with that is for brains, what matter are the connections. When you take it apart, there comes a point where you realize all you've done is get good at breaking it. So another approach is we could map it. We could learn the structure of the brain, because a map is a form of understanding. And the nice thing about contemporary neuroscience is we can do that. We've got techniques now to build incredibly detailed maps of the brain. But brains are dynamic structures. It's dynamic information flow. And a map, therefore, doesn't give you the dynamics. It's only part of the story. So another approach is we could observe brains working, and with contemporary neuroscience, we can do that. We can look at living neurons in living brains of living animals as they're doing their thing. The problem with that is there are so many neurons with so many connections that you really quickly almost start drowning in the volume of data that you're generating. There is so much detail, it's hard to step back and find the meaning of your system from the mass of detail of all of these neurons with all of these complex connections. And that's where the modeling approach really comes in. So model is really scientific jargon for best guess. It's a hypothesis. So when you're building a model, what you do is you take everything that you know about the brain, and you ask, how could this work as a system? The things that are known are what modelers call constraints, because the rule of modeling is you can't make anything up. You can't imagine connections that don't exist. You can't imagine neurons that aren't there. So within those constraints of the biology, that constrains the kind of model you can make. And then you ask yourself, okay, given these constraints, how could this work as a system? And that becomes your model. And once you've got your model, then your job is to test the model. And that's also not straightforward. To test a model, you've got to run a different thought experiment. You ask yourself, if this model's right, what have we learned from it? What can we infer from it? And then you test whether that inference is actually true. So to give you an example, I want to talk about the work of Mandayam Srinivasan, who gave a brilliant TED talk a couple of years ago. Now, Srini studies insect flight control, and he had a model of how insects control their behavior in flight as they're coming into land. But one of the weird consequences of Srini's model was that if his model was right, he proposed that insects aren't judging distance in meters or kilometers. They're judging distance by how much they've seen, which sounds kind of weird to us. So Srini designed an experiment to test how insects judge distance and found, yep, actually, insects aren't judging distance by distance, they're judging distance by how much they've seen. Now that finding didn't prove that Srini's flight control model was right, but it did mean there was no reason for Srini to imagine his model was wrong. And when you're modeling, being wrong is good, because of all the possible myriad ways that I could imagine a brain to work, if I'm wrong about something, I can categorically rule out all the possibilities I have now proven to be wrong. And I've also learned a new constraint. So what I can do is recast my model, taking into account this new constraint, and try again. And by iterating that process, you incrementally step closer and closer towards the truth of the system. But along the way, you're also learning what matters for your system from what's just detail. So along the way, you're approaching the truth, but you're also learning the meaning from the detail. Now, the beauty of this B-brain modeling project is what we will learn from it. So we will learn how intelligent, self-directed, autonomous behavior emerges from the circuits of the B-brain. Now, that's just B level, sure, but this project is not going to stop with a B. Because once we've got a model of a B-brain, we can use that as itself a model to explore how larger and more complicated brains could work, including our own. Now, I'm not saying that the human brain is just a big B-brain. That's absolutely not what I'm saying. But our brain, like the B-brain, is made out of neurons. And the neurons in our brain, the way they work, is actually very similar to the way the neurons in a B-brain work. And the way our neurons make connections and transmit information is actually very similar to the way neurons make connections and transmit information in the B-brain. But here's the kicker. Our brain is 80,000 times larger than the B-brain. So our brain contains 80,000 million neurons. That's an 8 with 10 zeros after it. So just take a moment to appreciate the scale of that number. Now, that is a legitimately dizzying level of complexity. And I would argue that we're never going to understand a system that complex by brute force alone. We've got to be smart. And one way that we can be smart is we could take our understanding of the B-brain and use that as a model for certain aspects of the human brain. So the B-brain model will become our first best guess. It will become our way in to start to understand the complexity of the human brain. And ultimately, that's why I'm building a model of the B-brain. It's not just to understand bees and their behavior. It's because ultimately, modeling the B-brain is going to help us understand the human mind. Thank you.